bidirectional path tracing. One of the two articles, one by Veach. Was there somebody else that wanted it? And is there anybody who is here today who wasn't here last time who wants to test? Okay. So hopefully my notes are in here, otherwise I'm in bad shape. Let's see. Here we go. Okay, so I was in the middle of doing a solid angle calculation. I forgot to do the hands up. Are we recording? We had a hemisphere, and we had a polygon. It's going to be easier if I just draw a triangle here. And we projected it first onto the hemisphere, and then down from the hemisphere. Say it looks like this on the hemisphere. And then we projected each of these arcs down. I should turn this out a little bit so I can see three projection lines. And we got something made out of arcs here, which are, as I said last time, since they're projections of circular arcs that aren't great circles, those circular arcs are going to project to elliptical arcs here. And so no matter what polygon we have, we can compute its area as a bunch of positive areas like this one, where this side is going around counterclockwise around the center, and negative areas like these, which would be subtracted to give what's left. And that works for any polygon, right? If you have, let me draw the circle, and let me draw a bunch of elliptical arcs here. Each of those elliptical arcs is either, well, let's see, how can I do it? I guess from the outside they're more like this. I'd have to think about what they really look like, but they could zigzag back and forth. And here's the center. And if I have the union of all the positive arcs, the ones that go this way, including, let's see, this one is also positive. So that means I've got this area twice, and then I subtract the negative ones. This one is subtracting all this extra stuff, and this one is subtracting this extra stuff plus that extra stuff that was double counted. And this one has been double counted but subtracted. And what I'll end up with is actually the actual area. Does that make sense? You have the positive ones headed clockwise, counterclockwise around their center, minus the contributions of the negative ones going clockwise around the center, and you get up what's left. You know, I'd have to look at each region here, but let's look at, say, this one. This one has, so what we really want is what was inside this polygon that was zigzagging back and forth. Now I have to remember what are my, here, this was my original stuff. So this one should not be there, and that's correct because it's positive ones and negative ones. This one should be there, and that's true because it's positive twice and negative ones, and so forth. And all these ones are positive ones and negative ones. So everything is going to give the right area. So that means we're reduced to the problem of computing for a single great circle arc here. Here's the sphere. Here is a single great circle arc on the sphere. Where will I draw it? Maybe like this. So actually, it's going to be easier if I draw the great circle that it's an arc of. So here's a great circle. Right, say starting here and ending there. And it's going to project onto this plane as a piece of an ellipse, right? We're seeing it foreshortened so that it actually looks narrower this way, but it's really narrower this way. Right? Because this is a whole diameter and this is less than a radius. And what we want to do is take an arc on this ellipse, say this much, and that's going to give a sector this much here. Let's see, the sector is maybe only this much here. So this arc here projects to this sector, and what we want to find is the area of this sector here. And the way we'll do it is we'll find the area of this sector here, and then we'll project it here. The fact is, this is a slanted plane. And if we have a normal here, there's some angle between, let's see, how do I want to draw it? It's an angle between the closest distance in this plane, which is, you go out perpendicular to here, and you're sort of getting the top of this ellipse, the part of the ellipse which is farthest. I mean, if I draw just a side view of the plane of the ellipse, here is the plane of the base, here is the plane of the ellipse, and this is the angle I'm talking about. Why don't I call it alpha? Right? And this angle is actually the, you could find that angle, let's see, what we really want actually is this angle, right? Because we want cosine. If this is alpha, then any distances here project by cosine alpha, right? Where alpha is the angle between this plane and the horizontal plane, which is the same as is the distance between the normal to the surface here and the normal to the arc plane. Right? That angle is also alpha because they're both complements of this angle here. And so if we have any area on this triangle, say we have on this triangle we're measuring a radius r here, and we look at a little piece which is, we're doing polar coordinates on this triangle. It's r d theta in this direction and dr here. Well, when we project that little piece, these sides which are, let me think, how do I want to do this? I guess these are tilted on the plane too. They're not horizontal. So what I really want to do is take a piece that's sort of perpendicular to this line and parallel to this line. The part that's perpendicular to this line will actually be horizontal on that surface, right? Because that would be into the blackboard, which is parallel to this line. So that piece would be projected to the same length, and this slanted piece would be projected to a shorter length by the cosine alpha factor. And that means the area is projected by a cosine alpha factor. It's like the projected area normal to the beam or something. That's that picture I drew. Whenever you have an angle between two planes and you look at the projected area in one to the other, it's by cosine of that alpha. Okay, so now what we have to do is find the actual area of the sector here that we're projecting. Whatever area we get for this sector on this plane here, it's going to project by cosine alpha to there. But on this direction, we have a great circle whose radius 1 and whose angle, say, is beta, which is the angle of that arc. Right? So the area of that arc is beta. And so what we have is the sum of beta cosine alpha, where this cosine alpha is supposed to have a sine factor to it, SIGN. Namely, if we get a plane where we're going around this let's see, which is having, let me get the formula with cross products and see if I agree with it. So basically, beta, say we have vertices, V1, V2, V3, and we look at the projected arc between the way I've drawn it, say, VI and VI plus 1 here. That's going to project onto this arc. Well, beta is the arc cosine of VI over absolute value of VI dot VI plus 1 over the absolute value of VI plus 1. So I guess if I do it that way, I'm not, and I have less than 180 degrees here, which is always going to happen, I guess, if they're both above the surface. Then I'm going to get always a positive dot product. So this part doesn't have a sign to it. But now what I want to do is I want to get cosine alpha as n dot the cross product, VI over absolute value of VI cross VI plus 1 over the absolute value of VI plus 1. Right? Because if I take two vectors in this plane, by the right-hand rule, their cross product is going to point up if I actually have a clockwise angle here. I mean, a counterclockwise angle. And if I have a clockwise angle, when viewed from above, that means the cross product, my thumb is going to be pointing down, opposite to the direction of n. So if I look at this plane normal, now it's positive if my arc is counterclockwise and negative if my arc is clockwise. So that means if this term is going to be the dot product of the normal with this normal to the plane of that slice here, that's going to have the correct sign to count clockwise negative and counterclockwise positive. So if I write the formula, then this sum is the sum over all edges of the polygon of arc cosine of, why don't I call this VI hat? It's unit vector, VI plus 1 hat. For that vector turned into unit vector times the normal dot VI hat cross VI plus 1 hat. So this is a formula for I equals 0, or say 1 to n, where when with I plus 1 is mod n. So it goes back to 0 for the last edge. So this is a formula for finding an analytic just with a few trig functions. Actually, this is the only trig function. This is just dots and cross products. I can find out the projected area of this, which we showed last time was equal to the form factor for a point, or infinitesimal area to find that area. And I propose that as one of the ways to do this gather of all the light coming in. And so one case that I think they mentioned in the book, or maybe I got it out of a paper, is if the polygon goes partly below this horizontal plane. I guess here's the polygon with straight line. You have to clip it with respect to the horizontal plane and get the piece of it above the plane. Otherwise, this part is going to count negative or something. And you can do that just by clipping the polygon with that horizontal plane. And I also mentioned at the end of the period, you can clip it with respect to all the other polygons in the scene that might be in front of it, in case it's not completely visible. Okay, so that is one method of doing the final gathering. But another method is just to do the sample the hemisphere and see what you hit and pick up that color, instead of trying to do it analytically. And did I mention you could also do it by a hemicube, right? Put a hemicube at every vertex and pick out the colors and multiply them by the hemicube delta form factors to get their solid angle contribution of that pixel. So now I want to talk about multipass methods. Oh, by the way, this formula and this projection is called the Nusselt analog or analogy. It's just a method of interpreting this formula in terms of projected area. So I'm going to follow the notation in the book. L is light sources. D is diffuse reflections. G is glossy reflections. S is perfect specular reflections. And E is the light source. Okay, and if I say something like L and then I put a D or S, this is like a vertical bar like the or sign in C, or G, and then I put a star, which means any number of powers, any number of a choice of one of these. That means basically any kind of reflection finally ending up at the E. This is the set of all paths that we should consider. And if this star is also a zero exponent, that means this product is empty. This is direct LE paths. And so what you want is that you find some method of computing the effect of all the paths. So a radiosity solution gets light and any number of diffuse reflections to the eye. You know, if you draw the light sources with a direct illumination, plus any number of bounces. But we talked last time about the kind of problems it has in being, has these Mach bands or discontinuities and, is biased. It depends on the way you formed your subdivision into polygons. But we talked about, let's see. Suppose we look at L, D, or glossy, star E. This is something you could do also by path tracing. The way we did it, in fact, this is what I suggested for a homework project, a final project for some people who didn't want to do something too difficult, and I also suggested it for people whose goal was to take our code so far and put it on a GPU, that they might implement this as well. And what that means is that we need a glossy illumination method. So just like we had direct illumination and indirect illumination, we would need a glossy illumination code. So I guess if I'm following the notation in the book, x theta. And so the pseudocode for this is, first of all, going to be Russian roulette. Less than the threshold, which you might make into the hemispherical integral of your glossy reflection. In other words, make it proportional to the power. Then you're actually going to trace it, otherwise you would write 0. So M is the perfect mirror direction. and we had the normal at x, and the direction that the light is supposed to be coming out in, theta. I guess it's at the direction, this is really y, right? We have to trace. No, this is the normal. Let me think about this. We had the normal, and we want the light coming out from x in direction theta. And instead of choosing a random phi, we'll choose a random phi based around a fine lobe at this mirror M, which is the mirror reflection in this incident angle equals reflected angle plane. I gave you a formula for how to do that you all used on your homework. Or maybe that was already built into the code you had. But anyway, this M equals twice phi dot n minus phi, if these are all unit vectors. Okay, and then sample psi by the Phong distribution. That means if you know M and you find a Phong lobe kind of computation with M as the North Pole, and you do that cumulative distribution of the marginal distribution of the angle away from the North Pole, just like we did for the cosine distribution, only now it's got cosine to a power. Right? I think I might have even done that integral on the board when I was getting the total energy of the Phong. But you just integrate up to a certain amount, and you have the cumulative distribution, and then you can sample the angles. And then around this way, the azimuthal angle around this North Pole is going from 0 to 2 pi. And use that cumulative integral thing to get how far away from M you should do it. You can shoot rays into this Phong lobe. So you trace a ray starting from x in the direction psi, and then you return compute radiance shouldn't take my picture away here. So anyway, you hit another surface, and here's y, and it's going in direction minus psi. So maybe I should keep that. Here is psi, and this one is minus psi. So I'll just continue my line here. Y minus psi. And we still need the cosine nx psi. But that's going to actually be times k spec. Let me think about this. I guess what we should multiply it by the Phong term, which is, what is it? Psi dot m cosine psi m to the nth power over cosine nx psi. Right. This is the Phong formula form, and that cancels this one, and then we have to divide by the threshold times the probability of choosing psi. And the probability of choosing psi, since it was based on this probability, is going to cancel this term too. And that's what we'll have left then. Right? So it's just similar to what we did for diffuse rays, except we're not the cosine distribution about the normal. It's the cosine to the nth distribution around the perfect mirror direction of your viewing ray. So that's a specular term, and now when we have this compute radiance in this direction, we'll get the further contributions, but we want to get contributions from Glossy too, so compute radiance has one extra term to it. X direction. So what you did for homework was estimated radiance equals direct illumination with X in the direction, and then estimated radiance plus equals indirect illumination, which is your shadow rays, and then estimated radiance plus equals, what did I call it, glossy illumination. So that's what you return. And I see I made a mistake here because I need an else here. Else return 0. Because this threshold is your Russian roulette thing. So you're going to do Russian roulette on that. So it's basically the same thing we had for the indirect illumination, but we're sampling it by the Phong, and because the direct illumination has a K diffuse and this one has a K spec, as long as K diffuse and K spec don't add up to more than 1, where they're really interpreted as fraction of energy rather than, directly multiplying the Lambert cosine, we're okay. So if we do that, then we'll get diffuse and specular. But the thing we won't get well is, first of all, it'll take us a long time. And second of all, we won't get the caustics from the light sources refracting or reflecting through shiny objects or, glass bottles or whatever. So the method of weighted ray tracing, let me just give summaries of other. Eventually we want to get all these paths, and we want them each only once, right? So when I was talking about just without this G, without this term, I was careful to make sure that we didn't double count like LDE, both as direct illumination and as sampling the light source by the diffuse. So if your diffuse sample hit the light source in this computation, we didn't want to include that LE, the emission from it. I probably shouldn't have erased this one, but let me erase all the way back now that I've started. And look at some more kinds of things. Weighted ray tracing. So what do we get? We get LDS star E. This is trace your rays bouncing off perfect mirror surfaces till they hit a diffuse surface, and then do direct illumination only from point sources with shadow rays. So L in weighted ray tracing is limited to point sources, but if you add on Phong shading of those point sources, you're going to get LGE, right? Because the Phong shading is for glossy surfaces. It's a bit inconsistent, perfect mirror reflections, but glossy highlights. But anyway, that's what your first assignment probably did if you added glossy highlights to it. Suppose we do what I talked about last time, final gathering. With BRDF of a radiosity solution what did I call it? L tilde of x. So what that means is that radiosity solution had all of the LD star to it, but then we get a D or a G or even an S, right? I didn't add on perfect specular, but you could have another term here with a perfect specular reflection term in exactly the mirror direction. And you could have a constant for the perfect specular. And the three constants, K diffuse, K for glossy, and K for perfect specular, would have to add up to less than 1 for conservation of energy. So you could add even perfect specular to this if you wanted for your final gather. So you're bouncing off either glossy or reflected surfaces, perfect mirrors, with ray tracing, as well as diffuse surfaces, and then you're getting the diffuse shading. And I guess if I say one or the other but not 0, I better add on LE, the direct part, because the radiosity solution has, let's see, no, the radiosity solution already has the direct illumination as part of it, but by saying this thing has got to be non-empty for one of these, let's see, we're only doing it one time, not 0 times, so I better add on the direct light source. So this is the final gather. I guess we could do, instead of distributing it, we could do an L, D star, S star, E. This would be, let's see, how do I want to do it? Yeah, this would be weighted ray tracing toward the perfect radiosity solution, right? So if you have a perfect mirror and you had a blocky radiosity solution, you would see it in the mirror or reflected among various cubes till you bounced off the cubes onto a diffuse surface, or spheres or whatever. So there was a paper, I guess I got the date here, SIGGRAPH 91 by Chen, Rushmeyer, Miller, and Turner, called A Progressive Multipass Method for Global Illumination. And I'm going to show you all the terms they got and show you that they get all of those eventually. But it took a really long time because you've probably seen for homework when you do something like distributed ray tracing, and they had a final gather in it that needed that. It takes a really long time to get rid of the noise. So what they did is they compute a radiosity solution with what they call extended form factors. And the idea is if you have one diffuse surface here and another diffuse surface here, what they want to get is all the paths between them that is either just directly between those two diffuse surfaces or reflected off a specular surface. So say you have a mirror in the room and you look at paths going through the mirror and to the other surface. Well, you can imagine, beyond the mirror is another copy of that polygon. And the boundary of the mirror cuts it off, but it's as if you had that polygon viewed through the mirror instead of just directly. You could compute the form factors to it. Or you could do it by ray tracing. In fact, we can have LD star onto a diffuse surface by taking recursive ray tracing until you hit a diffuse surface. And if we generated the form factors by the method I talked about a week ago, where you do it by picking your receiving patch and picking points on it, and shooting out in arbitrary directions. Now, I think I talked about it shooting, the patch that's emitting the radiation, when I was talking about the shooting method. I said you can put sample points on that and choose sample directions, and then go out into the scene and see what you hit. Well, if you go out in the scene with recursive perfect mirror reflection and see what you eventually hit as a diffuse surface, so you don't stop at the first surface if it's shiny, you reflect off of it. You only stop when you hit a diffuse surface. And I guess you could have to use some sort of Russian roulette if a surface had both diffuse and shiny component. You could use Russian roulette to decide how you would consider it. Either continue bouncing or stop and call it the hit. You can build up these recursively, these extended form factors. In fact, you could even do D, S, or Glossy star D. By shooting these rays as you hit a glossy surface, use that Phong distribution that I was talking about on the far right board to decide how you would continue bouncing that ray around the scene until you hit a diffuse surface, and record it as that diffuse surface to the shooting diffuse surface form factor. And that means for all I, you would get the form factor from AI to the AJ, which was the shooting one. And if you use those form factors in a radiosity solution, what that radiosity solution looks like is L, D, I guess what I have is some non-negative combination of G's or S's, and then D, and then to the I. Right? Because the last one, if you're going to look at that solution directly, you're going to get only those paths that end up at a diffuse surface. So between, let's see, maybe I should write it like this. Right? This says any number of bounces between a collection of diffuse surfaces. There has to be a diffuse surface right next to the light source to get the direct illumination on that diffuse surface as, the emit. Let me think about that. Does it need to have a diffuse surface next to it if you're doing the form factors directly to the light sources? So maybe I should do it this way. The light source is also considered as a diffuse surface. So maybe I should write it more like this. Put the D after it. And put a plus here, which means at least one. But that's not really going to give you good what are they called? Caustics. Because you're only getting this as a radiosity solution, right, on the D's. And then you really should be doing a final gather to get rid of the polygon edges, and you should do something else to get the glossy surfaces. So this could give you sort of an extended radiosity solution. Why don't I still call it L? I don't remember what I called it before, but let's call it L prime of X. Okay, so now I'm going to tell you the four terms he got. So the first is L, D, S, or G star E. And this is direct illumination rays in Monte Carlo path tracing. So the idea is you're going to do a final gather. You're going to do this thing, and you're going to, Yeah, I'm going to put the D in front because he has something else for the caustic. So this prevents caustics, right? This says that it's only direct illumination on diffuse surfaces. So I could have left this the way I had it before. Both begin and end on diffuse surfaces. So that's this has only got one diffuse surface, but it could be visible in mirrors. And so you're doing the Monte Carlo path tracing to the first diffuse surface, and then you're computing direct illumination on that surface. So that's for direct illumination viewed in mirrors. And now we'll have L, S, or G plus D, S, or G plus star E. That means either directly or through mirrors you're seeing a diffuse surface, and that diffuse surface has been illuminated by specular or glossy paths from the light source. So for this you need a caustic map. So they shoot rays from the light source at the glossy or mirror surfaces, or the smooth or translucent refracting surfaces, glossy, I forget what they called it in that paper when we had distributed ray tracing. What did they call those surfaces that were not diffusely transmitting but sort of shine, not a complete like ground glass that diffuses, but slightly ripply glass, you know what I mean? So that the transmitted ray is concentrated near that Snell direction because of the slight ripples in the surface, but it's not completely rough and diffuse kind of transmission. So that's what we're talking about for either refraction or reflection. So you basically store those photons somewhere where they hit a diffuse surface, and then this is the viewing either directly, because this star could be 0 of the diffuse surface, or by your Monte Carlo path tracing of the caustic map. And then we have L, S, or G star E. So I guess in their Monte Carlo path tracing, they are including those terms. No, I'm going to keep this here. When we do the Monte Carlo path tracing, we may hit a direct light source. And if we do get its LE. So if we hit a diffuse surface, we trace direct illumination rays. But if we hit the light source, we in this Monte Carlo path tracing from our eye on shiny surfaces, we include that direct illumination. So this is the LE term from the Monte Carlo path tracing. And finally, they include the progressive radiosity solution. So let's see, that's L, S, or G, or D star. Okay, so their progressive radiosity must have this D in it. Let me just make sure there's no double counting now, if I put that way. Oh, I see how they avoid double counting. D, S star. Well, probably this should be S or G star. Okay, so let's see. We're doing final gather. So this must be the final gather. And I'm going from their paper, so why don't I just keep it S star and see if it adds up right. So this is paths that have, so this is, it's again Monte Carlo path tracing, but when you hit a diffuse surface, you bounce to the next diffuse surface, perhaps through mirrors. And you only get this previous solution here which was the radiosity solution, on the second diffuse surface, not the first one. Because if you viewed it at the first one, it would be blocky. So, let's see. Suppose we have 0 Ds in this general expansion here. Then we'll get this term. And this will have all the terms with 0 Ds in it. If we have 1 D in it, we'll either get this one with a single D with at least an S and G in front of it, in the caustic map, or we'll get the direct illumination with no S or G in front of it, because we're only shooting our caustic rays at the shiny surfaces. And if we have okay, so these are the case with 1s, these are the case with 0, and this should be 2 or more. So if it's 2 or more, I guess we should be doing this or G here. 2 or more, and then this could be any extra more. And so we've got everything exactly once by looking at these 4 effects and adding them up together. So we're using the caustic map to get the caustics refracting, and we're using this one and this one. Then the caustic map and the direct illumination have everything with 1D. And this extended radiosity solution has everything else, but it's blocky. So if you want to see it on a patch that isn't coming from the caustic map or direct illumination, then you really want to do an extra final gather. So if you think about it carefully, it does include everything. And I had to think about it carefully. I was actually a reviewer of this paper whenever it was 25 years ago. And when I was rereading it now in the journal, I saw thanks to the reviewer who wrote 13 pages of handwritten comments, and that was me. So if you ever look this paper up, I spent a bunch of time trying to verify that they had everything counted right. And I think they didn't have everything counted right, and I pointed it out. In one of the images, you couldn't see the light when you should have, because they claimed to be showing this direct illumination LE term, but in that particular picture, but it wasn't. But you can't. In the end, when it was published, it had all the things counted exactly once. And so that's what you want to do if you combine a bunch of methods. You want to be really careful that you don't have any double counting and you don't miss anything. And I think by this reasoning to say this has all the ones with 2, between there and there they have all the ones with 1D, and this one has all the ones with no Ds. They're getting all the possible paths, each counted once. And that's how these this is just one variant of it, but there are multiple ways of trying to combine terms. And next time, I'm one lecture behind now, I'll talk about bidirectional path tracing, but it won't take a whole lecture, so probably I'll start catching up again.